Look at this slow-motion footage of a massive stone block slamming into the Earth. To the human eye, the matter appears entirely uniform. It looks perfectly unbroken, dense, and heavy. But zoom in close enough, and the solidity we experience turns out to be a physical illusion. Every piece of tangible matter is actually constructed from a dynamic, microscopic blueprint. We call it the atom. An atom is composed almost entirely of empty space. Within that void, you will find only 3 distinct subatomic pieces, known as the fundamental particles. These 3 particles are organized into a strict hierarchy of size, weight, and electrical charge, a specific arrangement that defines how different types of matter behave. This diagram maps the absolute center of our blueprint, the nucleus. It is a densely packed cluster sitting right in the middle. The first resident is the proton, carrying a positive charge of 1.6022 times 10 to the negative 19th coulomb. The proton also carries physical weight. It has a mass of 1.6726 times 10 to the negative 27th kilograms. Packed alongside are neutrons. A neutron is a strictly neutral particle. Its electrical charge is exactly 0. But put a neutron on a scale and it registers at 1.6749 times 10 to the negative 27th kilograms. It is nearly identical in mass to the heavy proton. Because these massive particles are firmly locked together in the center, this tiny nucleus hoards virtually 100% of the atom's entire physical mass. Rapidly pulling back from that dense core reveals a severe shift in scale. Out in the vast empty perimeter of the atom, tiny dots continuously race along orbital paths. These are electrons. They carry an exact negative charge of 1.6022 times 10 to the negative 19th coulomb. This creates a perfect mathematical symmetry with the proton's positive charge. Looking at this chart, you can see that symmetry vanishes when we measure physical mass. An electron weighs an incredibly small 9.11 times 10 to the negative 31st kilograms. To put those metrics in perspective, a single proton is a staggering 1,837 times heavier than an electron, and the neutron pushes that scale slightly further, sitting at 1,842 times heavier. We can translate these abstract metrics into a daily spatial arrangement by looking at a coconut. You have a hard, heavy central shell, representing the massive protons and neutrons locked in the nucleus. Out at the edges, fast-moving, lightweight fluid circles the perimeter, mirroring the speed and extreme lightness of the electrons. The atom's structure is defined by balancing physical opposites: massive, immobile anchors locked in the center, surrounded by weightless, high-speed energy racing on the outside. Stepping back from the coconut metaphor, let's look at the strict architectural facts governing these 3 fundamental particles. This matrix explicitly defines the division of labor. First, we categorize by location. The electron operates exclusively outside the nucleus, while both the proton and neutron are permanently housed inside. Next, we add their electrical identities. Electrons maintain a negative state, protons provide the positive state, and neutrons remain firmly neutral. Finally, we assign their mass profiles, finalizing the dichotomy between the incredibly light perimeter and the heavily weighted core. This spatial boundary dictates functional responsibility. The heavy, clustered protons and neutrons inside dictate the atom's raw physical mass and its core identity. Conversely, the incredibly light negatively charged electrons on the outside determine the atom's physical boundaries and dictate exactly how it will interact with other atoms. This specific division of labor, mass concentrated at the core and interactive charge defining the perimeter, forms the basis for how atoms bond, react, and create the world around us.